Sorry for the short delay. Now the setup is working. So welcome everyone to my presentation, Secure and Safe Updates for Your Embedded Device, with the small subtitle, and how to solve it with the Rogue Update tool. My name is Enrico Jöns. I'm an embedded system developer and system integrator working at Pengotronics. So embedded IoT stuff, well, do we really need updates for this kind of topic? And the answer, of course, is yes. This is why we are all here. And yeah, at least the events that took place in October last year, when those small IoT devices broke down parts of the internet, that showed the last person that security, especially for these devices that become more and more connected to the internet and all infrastructure, that security is a topic of high priority. So connected with security, there's always the need for updating, because if we detect a security hole somewhere, we have to update the device. And what other reasons do we have for updating? It's obviously for fixing bugs if the software does not perform as we assume it to, or if we want to add new features to an existing device. So a short structure of the talk. The first chapter will be a bit about general challenges in updating and give a short overview of that. Then I will introduce the Rogue Update tool, and then hopefully the time is not over then yet. I'll show a short demonstration, a live demonstration, so I hope it will work. And at the end, I give a short, very short conclusion and summary of what you have heard here. So updating, you might think, is very simple. So you just have a few steps. You have an update and load it on your system. Then you perform the update, write the changes to your system, and maybe you reboot the system and everything works and is fine. Well, as usual, reality is not that easy. So especially on embedded systems, you have different devices you want to update, for example, a NOR flash or an SD card with different partitions on it, and you have to find out what to update there. And then you don't know who is the author of your update. Is he allowed to update your device? And are you updating the right device with the right update? And you also need some interaction with the bootloader. And if you've done all this stuff step by step, then suddenly someone plugs the power cable off and everything breaks down completely. And you don't have real direct access to this. So the main question we try to answer here is, what is so special on updating embedded devices, and why don't we simply write it in a short bash script? So updates, you may know from your daily use, you use some kind of packet manager like Aptitude or something like this, and you update your system, and yeah, in most cases it will work, and if it does not work, okay, you fix it. So what is the difference when you have an embedded system? Well, on embedded systems, you don't have direct access to the device. So in most cases, you don't have any access to this. And the only way you can start your update is either by plugging in a USB stick or by starting a remote deployment via a network. And then all you can do is watch a progress bar, and at the end, it either succeeds or it will fail. And if it failed, you really get in trouble, because you don't have any chance to recover it. You don't have any easy access to the device, and will cost you time and maybe money to recover the device. So what are the key requirements for updating an embedded system? First of all, the update process itself should not fail. And in case it does fail, the system itself should still in a state where it can be updated. And you also want to recover from runtime issues when your system suddenly stops then there should be some mechanism that reboots the device and brings it back into a state where it's still operating. Apart from the safety aspects, you also want some security aspects, as these devices normally operate in some areas where you don't have direct access and you can't control who accesses the device, and you have to prevent the device from unauthorized access or updates. And there are some further limitations, like you have some sort of storage that is not that easy to handle, and limited resources, limited bandwidth, etc. So one golden rule for updating an embedded system to not make it fail is to only install well-defined states. So this means the entire state with all components tested together. And the the major rule we have when updating an embedded system, we do not want to break the device. We have to do everything to avoid this. So how to avoid this? So let's talk about redundancy. The simplest redundancy mechanism is when you run from a system that has no redundancy. So you perform an update, and if there is a power loss or some issue during the update, then the device might not be able to boot, or the update system might not work again, and you have no chance to update it again. So you have to call the server technician. Better approach is to use an asymmetric redundancy mechanism. This is especially good for devices where you have limited storage capacity. So you have a small dedicated recovery system where you boot into when you want to perform an update, and you can perform the update, and even if the update of the system itself fails, you can still boot into the recovery system and perform further updates. So it's updatable in case of a failure, but you don't have an operating system if the update fails. So what we really want to have is a full symmetric redundancy system where you have a system A that may update system B, and a system B that is able to update system A. And even in case of failure, then you have maybe an old, but you have one system that is still operating. So another thing that is really important when updating is atomacy. The result of the update should either be the update succeeded or the update failed. And you don't want to leave it in an intermediate state where it's not defined. So how can we achieve this? Here's an example. You start your update from your running partition A, and you have to see the entire update as a critical operation. If something fails during this, then you have to roll back, or you don't have to break your device. So what you normally have is some kind of switch where you can say, okay, boot from system A, and then you turn the switch over and say, now boot from system B. This is normally done in the bootloader. And this operation has to be done at the very, very end of the update process, as the last operation. Only there you can be true that your update was performed successfully. And it should be itself an atomic operation, of course. And you also want to security. You don't want someone unauthorized to be able to update your system. There are two basic ways to achieve this. The first of is you use a trusted transport, like in WebCase, for example, SSL, HTTPS. Then it does not matter really if you trust the update itself. You know it comes from a trusted source. This works well for the download case, but it will fail in the USB stick case. If you plug in a USB stick, you don't have easy mechanisms to trust the USB stick. So a more general approach is to put the trust in the update itself and sign the update. Then you don't have to trust your connection, and this will work both for downloading and for the USB stick case. And another thing is that you also don't want to unattendedly update a device with the wrong software, for example. You don't want to turn your toaster into a printer by an update. And one could think, okay, I just check the hardware if it's the right hardware I write to, but this will not work in all cases. As you have here, basically from the outer view, the same hardware, but it works as a different product. So a very simple and thus most times the best approach is to use an explicit identification that you place on the target and on the update. So here this is PyToast 2000 and PyPrint Plus, and if I say it's an update for PyToast 2000, then it's clear it's for this. You can check this and not for this. And another task that your update system has to handle is that you have to find out where you update. So you have an image B, and you have to say, okay, is it a bootloader image? Is it a bitstream image? Or an other image? Is it for the first, or it's for the second redundant partition, and the same for the root file system? And this works only if you have some kind of configuration, either only in the update itself or in the update and the system itself, so that you can match these partitions. And there are a lot of other things you have to take care of. You have to do good error handling to be sure that nothing in the update process failed. You have to think about where do I store my data? Do I store it in a single partition or in a redundant partition? This matters if you deal with fallback or data migration, because the system A and B use slightly different data formats, and watchdog handling and much more. So as a conclusion, you can say updating is not that easy. And this is why we developed Rauk, the update tool in firmware. So short overview, it's licensed under the LGPL 2.1, so it should be easy to use it in your application or in your product. It's C code built based on glib and packaged with auto tools, so it should easily build. And Rauk you can compile as a host tool. Then it is used to create, to sign, to re-sign, and to inspect updates for your device. Updates in Rauk we have called bundles. And you can compile it for the target. Then it operates as the update service on the target that controls the entire update process, the installation, communication with the bootloader. And it also provides a small command line tool that allows you to easily install a bundle from the command line or inspect the system or updates. Yeah, here's a short overview of how bundles look. You have your images and bit streams, for example, that you want to install. There's some information extracted and put in the manifest for verification. And this all is packed together in a SquashFS. We have used SquashFS as it provides good compression and as it is mountable, so you don't have to unpack data and thus store data capacity. And these are signed with X509 signatures you know well from SSL. So, and the idea of a bundle is that the bundle describes the entire intended state the system should have after the update, and then the Rauk service takes care of how to achieve this. This is a bit about handling in Rauk everything that could be a target for installing something we called a slot. And then you can create in your configuration classes of slots, for example, application file system, a root file system, and instances of the slot. And this is used by Rauk to match what you have in your update bundle, where you have an image for a specific class, to the real device on your target. That's one of the core algorithms that Rauk provides. Here's a sample configuration. This one is the system configuration. This is normally stored on the target's root file system. We have some basic information about the system, about keyring, and here defines the slots that you may update. And then you have here the update manifest. You can here see the compatible that has to match between the target and the update itself, and the image description of those images you want to install. For example, here this root file system image would be installed on one of these slots, depending on which is detected as currently inactive by Rauk. If you want to use Rauk in your next device, we have Yocto integration in our MetaPTX layer, which will soon become Meta Rauk. We have PTX-dist integration currently only on the mailing list, not in PTX-dist mainline, and you can also integrate it manually. And here's a short overview to give a basic idea how it's used. This is the Rauk bundle command you use on your host to create the bundle with a directory that includes all the content you want to bundle. And on the target, you simply execute Rauk install. Or if you have an application, we have a dbus interface where you can trigger the installation from. So let's check the time. How much may I exceed?
2 minutes.
2 minutes. The previous talk was exceeded too, so
okay.
A bit, I hope. Yes, thanks. So the demonstration you may all see here, these are 6 Raspberry Pi currently running a PTX-based image, and this includes the Rauk update tool. And I try to trigger the update before continuing the talk. Thanks.
Unfortunately, we don't see your desktop.
Yes, I know. But I'm not sure if they. So what these devices are currently connected to Hogbit update server. Oh, yes. Now I know what you're talking about. So I shortly describe the setup. We have currently a PTX-based image running, and these devices here are connected to a Hogbit software deployment server. And on the devices, the Rauk service is running, and a little Python script that shows these small PTX-dist images. And the presentation or the demo should now show that I deploy a Yocto update on these devices. Yeah, this is what I wanted to show here, but I think the setup did not entirely finished because of the irritation in the beginning of the talk. So if you want to see the demo working, maybe you would like to join me after the talk. I try it in a few minutes. Yeah, this is the basic layout of the root file system on the Raspberry Pi. You have easy redundant system and the barebox bootloader with its boot state framework running on it. And yeah, this shows that the update system is really independent from the integration, and it can easily be integrated into different needs, and it's generic, so it is designed to be adaptable to exactly your needs. So I can't switch to the next slide, but it should be the conclusion. So I have to try it manually. So it works. So what are the basic facts that we have learned? Updates, especially on embedded devices that are connected, are mandatory. The second one is that updates are not really trivial. There are some pitfalls I've shown and some more I have not shown yet. And if you do updates, only install well-tested software sets. So this is the best way to not break your device. And, of course, use free and open software update frameworks. For example, I give you an idea, Rauk would be a good choice. So thanks to everyone. And I think the time for questions is, yeah, okay. So if you got questions, just come directly to me and we will discuss it.